Yeah. We are starting with the recording now. Yeah. Anybody else has a question?
So, good evening, everyone. Since we have started session, would like Pantho to introduce his team and start the session and Q&A session, etc. Thank you. Over to Pantho.
Okay. Thank you, ma'am. Okay, so welcome all to the session number 3 of Fundamental of Particle Physics workshop. Your peer tutors are me. I'm Pantho Chakravarti. I'm a second year physics major from Shibnada University. With me, there's Dibangi Agarwal, who's also a second year physics major, and we have Uday Bhanu Singh, who's a graduate from SLS. Before starting, we would like to thank Rachna ma'am and Vinita ma'am for making this possible, and also special thanks to our professors, Dr. Arindam Chatterjee and Dr. Kenji Nishiwaki, for performing the original webinar, after which we decided to do this workshop. Okay, so Uday, would you like to brief?
All right, thank you, Pantho, and thank you so much, everyone, for showing up. It's really motivating to see so many people on the screen right now. We're all glad that you're attending the session so diligently. So before we begin with what we had planned for today, we wanted to do a little recap of what we covered in the last session. Someone say, is anyone? Yes, we are speaking. Can you hear us? Am I audible to everyone?
Yeah, you are audible. Maybe
Okay.
you can check your connection if you're not able to hear us.
Yeah. All right. So I'll continue then. I hope the issue gets resolved soon. So yeah, we want to do a little recap of what we covered in the last session. So if I believe a lot of you were present in the last session as well. So does anyone want to share a quick briefing about what we covered in the last session? Anything that you remember? Anything important that you took away from it? If anyone wants to uh, give a very brief summary. Okay, I think Urjit Mahajan is raising his hand. You can go on.
Thank you for the opportunity. So we studied about the different parts of the standard model. So as in quarks, leptons, and the gauge bosons and the scalar bosons. And then we further moved on to the fundamental forces and also how they influence the nature and the existence of particles, and also how their intensity and their strength varies across.
Yep, that's right. That sums up a large chunk of what we covered. So as Urjit said, we talked more about the standard model. We talked more about the particles, and we went a little deeper into the world of quarks and leptons. We talked about the different flavors that the two have, and we also talked about how the quarks interact with all the fundamental forces, whereas the leptons do not interact with the strong force. And we began a discussion on the fundamental forces as well. Before we could close it, and that's where we'll pick off from for today, from like after this recap. So yeah, before I hand it over to Pantho to take the session forward, I guess we can ask if anyone already has a question on what we covered in the previous class, so we could quickly resolve them. If anyone has any questions, you can go ahead. Otherwise, we can move on.
I guess we can move on then.
All right. Okay. So, Pantho, over to you then.
Okay. Shall I share my screen?
Yeah, please. Yes, somebody raised a hand.
I had actually raised my hand by mistake, sorry.
Okay, it's okay.
Is it not visible?
No, your screen is not yet visible.
Okay, wait, I'll try.
Yeah, it's visible now.
Okay.
Okay, so I'll start. I'll start from the fundamental forces only. In the last class, we saw how the ranges of the fundamental forces and how the relative strength worked. So basically, to recap, the strong force is the strongest one. Then next is the electromagnetic force. Then there's the weak force, and last is gravity. Gravity, as you can see, even though it has infinite range, it is the weakest of the force, and the other infinite ranged force is the electromagnetic force. So, okay, next slide. Okay, so the first we go to the electromagnetic force. It explains how stationary and moving charged particles interact. Then every charged particle gives off an electric field. Electric field is basically it's similar to a magnet. It attracts the negative charged particles towards it and repels all other positive charged particles. So that's an electric field. An electric field is basically if you are in a particle's electric field, the particle can exert force on you. That's the basic definition of a field. So then there's the magnetic field originates only in moving charged particles. So like electric field will be created no matter what the particle is doing, whether it's stationary or moving. But magnetic field or magnets will only be produced when the charged particle is moving. So this force keeps the electron in an orbit around the nucleus, and the carrier for this force is a photon, which is basically the particle of light. After this, we'll watch two videos which will briefly explain what the electric field and the magnetic field is. Devangi, next slide. So the electromagnetic force, it actually contains two forces, the electrostatic and the magnetic force. Here we'll watch videos describing each of them. So please start.
We have electromagnetism to thank for a lot of different things, from like allowing you to watch YouTube videos on a computer that is powered by electricity and holding all of the atoms in the universe together. But electromagnetism, as the name implies, takes two forms that look totally different to us. We have the electrostatic force and the magnetic force. But don't be fooled, electricity and magnetism are the same freaking thing. Weird, I know, but since this is my show and I can do what I want, I'm going to break this up into two episodes, one on electrostatics and one on magnetism. First, electrostatics, the cause of lightning and balloons sticking to me. As you probably know, electromagnetic force acts on objects that have electric charge. In electrostatics, they're described as either being positive or negative. Objects with opposite charges produce an attractive force between them, while objects with the same charge produce a repulsive force. The greater the charges, the greater the force. And the greater the distance between the charged objects, the smaller the force. All this was laid out nice and simple by French physicist Charles-Augustin de Coulomb in what we now today call Coulomb's law. Coulomb's law is able to describe how protons in an atomic nucleus, which are positive, keep negatively charged electrons from just wandering off. And just like with other fundamental forces of physics, there's a special particle that conveys this force. Here, you've actually heard of the particle. It's called a photon. Photons carry the electrostatic force between the electron and the proton. Photons are the same particle that carry light and heat, which is why electromagnetic force is able to travel at the speed of light. Now, electrostatic force is called static because it can build up in an object, creating a ton of potential energy that's just dying to move someplace. Take this balloon, for example, and my wool sweater. They are both made up of atoms, as you might imagine, and atoms normally have the same number of electrons and protons, so they're electrically neutral. But some substances tend to take on electrons really easily, like rubber, while others tend to give them up, like wool. When substances with these opposite tendencies come in contact, the electron from the atoms of one substance jump into the atoms of the other. So when I rub the balloon on my sweater, The balloon gains electrons, becoming negatively charged, and my sweater loses electrons, making it positive. Now, it might look like the friction of me rubbing this is causing the charge, but that's not true. Rubbing is just putting the atoms into contact over and over again, making it more likely that they'll swap electrons. The more they swap, the more charge gathers in one place, and the two oppositely charged objects cling together. They're effectively just sharing electrons when they touch. The same thing is going on with lightning. Electrostatic force builds up in rain clouds as they rub together. Once enough electrons are built up in the clouds, they need to go someplace that has a bunch of protons to neutralize them. So the atoms in the air basically serve as a path to deliver these built up electrons through the sky from their negatively charged source, the clouds, to their positively charged destination, whether it's the ground, another cloud, or some really unlucky person. So electricity is just a stream of electrons trying to get from a negative place to a positive place. And isn't that what we're all trying to do, really? The crazy thing is that once electrons start flowing like this, it creates a magnetic field. And what? But that is why next time we're going to be talking about the magnetism portion of electromagnetism. Thank you for watching this episode.
Okay, so you guys have any questions related to this video? Yeah, go ahead. Somebody unmuted themselves, right? Yeah, I can see a hand raised.
I had a question, but it's not directly related to the video.
Yes, ask.
Okay, so my question was that I just wanted to confirm. So it means like the stronger the particle force, the harder the object will be to take apart.
Excuse me, can you repeat?
Yes, I actually wanted to confirm something. So I was a little bit confused, and I wanted to ask that I understood that I think that like so the stronger the particle force, or the harder it is to tear the object apart. Is that?
What do you mean by particle force?
Like I'm not able to explain what I mean, so I just I'm not really able to phrase it properly.
I think he's trying to say that when two objects have a stronger force, then it's more difficult to pull them apart.
Yeah. The stronger the force between two objects is, the more difficult it is to bring them apart. For example, you and the Earth. Like, why do rockets take so much fuel when going out of the Earth's atmosphere? Like, it's all they're all trying to get away from the gravitational field, the gravitational force that the Earth exerts. For that, they need to burn a lot of fuel, because otherwise they won't be able to leave. Like, the most that we can do as humans is like they jump, and that's like a few microseconds freedom from gravity. That's it. So we need a much more powerful force if the force between two objects is strong. In fact, it's equal. Like, you need to put an equal amount of force in the opposite direction to get away from a force. Okay, does that answer your question?
Yes, thank you.
Okay, cool. So any other? Yeah,
go on. Sorry.
Yeah, any other question? Okay, cool. I guess then we'll go to the magnetic force video.
Okay, so I'll continue then.
Welcome to our second episode on electromagnetism, one of the four fundamental forces of physics. Like I said last time, there are two aspects to electromagnetic force. Electrostatic force, which builds up a charge in an object and can travel in the form of an electron stream, and magnetic force, which is responsible for the way magnets work. But even though their effects look very different to us, they are in fact one and the same. Hopefully you remember that electromagnetism acts on objects that have electric charge. This charge creates a field around an object, but a magnetic field is a little different from an electrostatic field. For starters, unlike a charged particle, which can either be positive or negative, a magnetic field has both a positive and a negative area, what we call north and south poles. Magnets always have both poles, no matter how many tiny little pieces you cut them up into. But magnetic poles interact very much like single pole charged particles. The same poles repel each other, and the opposite poles attract. And just like with electrostatic force, because it's the same force, magnetic force is carried between objects by photons. To demonstrate that electrostatics and magnetism are, in fact, effects of the same force, you can create magnetism using electricity. A simple electromagnet is just a coil of wires which, when a current is passed through it, generates a magnetic field. You can make one yourself by passing an electric current through a wire wrapped around a nail or a screw. Switch on the current, and the screw becomes a magnet. Switch it off again, and the magnetism disappears. The magnets on your fridge are made basically the same way, only with a lot more electrical power and using special materials to retain the magnetism. And hey, you know what else is an electromagnet? You're living on one. The constant churning of the molten iron in the Earth's outer core creates electrical currents, and those currents generate the Earth's magnetic field, which has proven to be super useful for things like navigation, and since the magnetosphere is what protects us from solar wind, not being dead. So if an electric current produces a magnetic field, the reverse must also be true. And in fact, yes, you can generate an electric current using a changing pattern of magnetism. If you put a coil of wire within a magnetic field and continuously spin the wire or the magnet so that the magnetic field inside the wire fluctuates, electricity will flow through the wire. And this is really exciting because it's the reason why we have electricity. All you have to do is keep the wire or the magnet moving and you'll have a continuous source of electricity. Stop moving and the electric current will stop. This is how pretty much every source of electricity in the world works, from wind turbines to hydroelectric dams to coal with nuclear power. The only big exception is solar power, which is really interesting, so we did a whole episode on it. Which brings us to the conclusion of our series on the 4 fundamental forces of physics. If you have watched all of them, now you are a master.
You can stop the video now. It's just the end credit. Voila. Okay, so any questions about magnetism or electrostatic, like the whole electromagnetic force as a whole?
Hello.
Hello?
Oh, so are you able to hear me?
Yeah, now it's better.
Yeah, previously I was speaking, but I guess you were not able to hear me. So I had a question related to electrostatics, that which thing determines that how much stronger the force would be of the particles?
It depends on the electric charge. Your electrostatic force, it depends, like force between two charged particles depends on the charge of each objects and the distance between them. So the Coulomb's law, like the Coulomb force, which we talked, which you saw in the last video, it can be expressed as some constant multiplied by the product of the two charge of the particles divided by the distance of, like, the distance between them squared. So if you have a huge charge, then it gives a higher force. Or if you have like not a much of charge, but they're very close to each other, then also the force is very strong.
Okay, thank you.
Anything else? Yeah, Arav?
Sir, so I didn't understand something about magnetic force.
What?
Like, if I take two magnets, why do the similar poles repel with each other?
It's similar to why positive charges repel each other and the like charges repel each other and the unlike charges attract. It's basically, it can be considered as your magnetic fields, the field of the magnetic field. You've probably seen diagrams and all which has like loops around the magnet, right? Like have you seen like or even the Earth's magnetosphere? Like you have seen the rings around the object.
I've seen that. Yeah.
Yeah. So that basically says that the magnetic field starts at your north pole, and it goes and it travels and enters through the south pole, creating a loop, so that your there's no you don't lose any energy. That's why magnets can never be monopoles. That is only one pole. Because a magnetic field will always have to become complete a loop. Because of that, so because of that, when two north poles come closer to each other, because both of them are releasing the field, there's no one to complete. There's no one to complete the circuit, so they repel each other.
Okay, I think I understand.
Okay, so now I guess we'll move to the next force.
Okay. I think someone else also raised their hand.
Okay.
But if not, then maybe we can move
Uh,
on.
yeah, anybody who has raised their hands?
No one? Okay, maybe we can move on then.
Leah, Nagpal, someone. I can see one hand raised.
Yes, I had actually asked a question previously and I didn't lower down my hands.
Oh, okay, it's okay. Okay, I guess we'll talk about the next force then. Next force. Yeah. So now we come to the strong force, the strongest of the four fundamental forces, and it's actually the bit of it's complicated than it's more complicated than your electromagnetic force. So the strong force, in fact, actually has two forces in it. Like there are two forces which constitute the strong force. First, we'll talk about a force that's called the color force. This is the color force. After this, we'll talk about the other one. Okay, so this subpart of the strong force is what keeps the quarks bound to each other to form protons and neutrons. You guys all remember what quarks are, right?
Yeah.
Okay, cool. So this force basically bounds the quarks together, and after that, I'll introduce a term called color. So color is a quantum state that quarks have. There are three colors: red, blue, and green. Now this is a misnomer because quarks fundamentally, physically, quarks cannot have colors because the size of the quark is smaller than the wavelength of your visible light. So technically they can't have colors, but because scientists are awesome at naming things, they just named it color. Okay, so for proton or neutron, any kind of three quark hadron, your hadron should be a white colored. It's just a convention that the physicists used. So for that, there are three like in the color wheel, there are three primary color of light, that is red, blue, and green. You guys might have noticed your like the old fashioned TVs also had like red, blue, and green colored rods. So when you mix these three colors, you get white colored. So color as a quantum state, or like quarks have this quantum state called color, and it does not depend on the flavor of the quark. That is, the quarks, like the color changes between the three quarks, and it always changes in such a way that the total color of that particle, that is proton or neutron, is always white. So quarks, so basically that quarks are always changing color by exchanging gluons. Gluons are the force carriers for the strong force. So they're always changing colors by exchanging gluons, and this in turn holds the quarks together. So the gluons change the colors of the quark that they leave and the one that they go to. So for example, if you have three quarks, or be a proton or a neutron, if a quark, if a gluon leaves this one and goes to this, the next gluon, then it changes the color of the previous gluon and the previous quark and the quark it goes to. So that's how like the gluon just passes through, like it just travels between the quarks and it changes color in such a way that the overall colors are there are always three distinct colors in the particle, and like the proton and neutron. So that's how they hold the protons and neutrons together. So that is the color force. Now, do you guys have any questions? This is weird stuff, I know.
I have a question.
Yeah.
My question was that I did not understand how quarks keep changing color.
Okay, so color. Okay, first of all, don't think of it as colors that we know or we see. It's not that color because quarks fundamentally cannot have colors. So this is just a name that the scientists used. So basically, just think of it as a property. So for example, like you can substitute it with anything. You just have to know that there are three types. There are three types of color. There's a state which can have three values. for example, X. You guys might know like polynomials, right? So consider that it's a polynomial where the X has 3 values. So
I actually.
Can I explain, Pantho, with your permission?
yeah, sure, ma'am.
So, what's your name, child?
Ma'am, my name is Alia.
Alia, I just love your question. You know, when I was in that grade, probably I would not have had guts to ask such question. And I really salute your, inquisitive mind, bacha. Always ask question. Always. So first of all, Pantho, what Pantho sir is saying is very right. So with his permission, I just want to simplify a bit, Pantho. Am I allowed?
Yes, ma'am. Yes, ma'am. Go ahead.
So you understand like this. Suppose you guys are in school, right? And when you go to school on a specific day, you have to wear yellow t-shirts, red t-shirts, green and blue t-shirt. Yeah?
Yes.
Because
Yes.
you belong to different houses, right?
Yes, ma'am.
Yeah. So when you are in yellow house, it means your house have got some certain specific, talent, or you have fascination for that house. It doesn't mean that your original color has become yellow. Are you getting it?
Yes, ma'am.
Just to distinguish you from the blue house and red house, since you are in yellow house, school asks you to wear yellow t-shirts.
Yes, ma'am.
Are you getting my point, bacha?
Yes, ma'am, I
Yeah.
am.
So your team, since you are in yellow, house, you are different from red, blue, and green because these teams are different and you are different, right? But
Yes, ma'am.
basically, there is no as such color, your skin color or something. So it is something like that.
Yes,
Am
ma'am.
I getting it?
Yes,
Yeah.
ma'am.
Thank you so much. Please go forward. Panthu, this I believe she must be in which grade you are in?
I'm in grade 6.
Grade 6. So I think she will not, don't go much in detail of polynomial and all.
Okay,
Although you
ma'am.
are explaining perfectly all right, and I'm really impressed, Pantho, with you.
Thank you, ma'am.
But
Thank you, ma'am.
you just explain like the way children understand. Thank you.
Okay, ma'am. Okay, so does that answer your question? Like, do you understand it like somewhat?
Yes.
Okay, good. Urjit, you have a question?
Yes. So I just wanted to confirm. So the number of gluons in an atom, in a collection of quarks remain the same, right?
Yeah.
Okay.
Like, yeah. So basically, the gluons just keep traveling between a proton or a neutron, and it just keeps changing their colors. Okay.
Okay. Thank you.
Okay. Cool. Any other question? Any other person who has their hands raised? I can't see.
I had a question.
Yeah.
Does the three like except obviously there's a name for each quantum state that the quark has. So there must be some difference that is. So what does each color signify? Like what changes in each? Is there any change in each quark as the gluons keep on traveling between them? Is there any change in some property, or because then if not, then what is the significance of naming the three colors?
Okay, so once you dive deep into more particle physics and all, you'll see a lot of states and all. They have mathematical meanings. They don't have a lot of physical meaning. Color is one of the similar things. It does not have a lot of physical meaning. It's just it was seen that the gluons travel from one gluon to other, and colors also come in when we talk about antiparticles, antiquarks, and all. So just to make sure, just to define the path of the gluon, the color, the quantum state color was created. So it does not have any physical meaning as such.
Can I again? I'm sorry, but can I again? Make it simpler, Panthu, with your permission.
Yes, ma'am.
So it is something like that. That the way it behaves, you can say, the way it interacts, the way it behaves. So when you say physical meaning and why this color, why that. So again, I would like to give the same example of that. Suppose there is a inter-house competition happening in your school, and yellow is fighting against blue. So they are on opposite side of the court. So how this yellow behaves, because they have to, go to the other basket, this have to go that side, how they interact. So same way this quarks also, when you say colored and all, how they behave at a particular situation, how, depending on that. So this color actually means, the root of all this is same, is how they behave. You go to the macroscopic level, you go to the charge, forget about quark, positive and negative charge. Each charge has got 1.6 into 10 to the power minus 19 coulomb. Yes or no?
Yes, ma'am.
Value is same, but how positive behaves and how negative behaves in an electric field, right? So basically, if you see the value of coulomb in terms of value is same, but how they behave based on that, they had been named differently, and obviously the mass and all also is different according to it. So what Pantho sir is trying to explain is exactly same, right? So thank
Can
you.
I just
Please
chip in for one little thing?
Yeah.
I'm sorry, Pantho and Vinita ma'am, with your permission. See, the very fact that the quarks have been given red, blue, and green color, and these are the primary colors of light, right? The red, blue, and green together make it white. Now, when the quarks are doing their job inside, and they're pretty naughty people, it's very difficult to predict where one is going to be and how they are going to behave. So when one goes to the other, suppose the color changes. Now, the others will also change so that the basic combination remains white, and hence the color change thing is coming up over here. I hope that was helpful.
Ma'am,
Yes, yes,
ma'am, it was
Rachna.
helpful. Ma'am, that was helpful. But my basically what my question was
See,
that
see,
all the
probably
color
see.
changes obviously.
The thing is, we're talking at the quantum mechanical level. Here, the particles, the entire topic of our discussion is not classical physics. If we are going at the quantum level, here the particles do not behave the way we know them to behave. Over here, if we have to throw big words, we'll say there is an exclusion principle coming up. It's difficult to predict where they are going to be, and so on. So hence, they have to, their spins are going to be different, their orientations are going to be different. These things take into account, and on the basis of these mathematical aspects, like Pantho said, they are given the red, blue, and green color. And when they are moving, they change one of their properties, due to which, now the color assigned from red becomes blue. So the other will also change color so that the total remains white. So something like that is happening over here. So the story at the quantum level is very different from what the world that we know. And that makes the entire study of particle physics so challenging, at the same time intriguing and interesting.
Also, Pantho, I feel that this child is really want to investigate and explore more and understand the complexity of all this. You are most welcome. You also do research and we'll sit one-to-one and understand.
Yes,
Is that okay? Because
yes,
the type of question you are asking, I really have high regard for you. It's pretty high, and we wanted to explain it so that everyone understand. In the meanwhile, you must get satisfaction of exact answer you want to know. You also research, and probably one-to-one, Pantho, and you will sit and he will explain.
Yes, ma'am. Okay.
Thank you. Over to you, Pantho.
Thank you, ma'am.
May I ask
a question?
Yes. My question was that my question was that what properties do the quarks exchange if they are named out of colors only to identify and differentiate them or to other particles? So what properties do they actually exchange then?
It's very similar to the last question only. As such, physically, they don't change a lot of properties. It's just like charge. Like charge can be positive and negative. There are two types of charges. Similarly, another thing that the quantum, like the quarks have, that is the color red, blue, and green. So that does not signify anything. Like we can't explain it by any kind of way in the physical, in the by classical mechanics, and according to quantum mechanics, it's just maths.
Okay, thank you.
Okay. Yeah.
Sir, I also have a question.
Yes, go on.
Sir, I didn't understand what are these gluons, quarks, and hadrons.
Okay, so gluons are bosons. Were you there with when we had the last session?
No, I'm here for the first time.
Okay, so that is a thing. Okay, so in the last class we discussed what are gluons. Gluons are basically they're a part of bosons. Yeah, bosons. They're the force carriers and who mediate the fundamental forces. Initially, according to classical mechanics, we knew that for forces we don't need particles. But after whole quantum mechanics and all, we realized that no, the forces are also mitigated by particles. So bosons, gauge bosons, are basically those particles which transfer, which make the forces act between two particles.
Okay.
So there are 4 types of gauge bosons and one scalar boson. We'll talk about the scalar boson later. So basically, in short, there are 4 bosons: photon, which is electromagnetic force and which is the particle of light. There's gluons, which controls the strong force, and W and Z bosons, which mediate the weak force. Okay. Okay. So we'll now move on to the next part of the strong force. Yeah, the next part of the strong force is the nuclear force. This strong force is felt between the nucleons, the protons and the neutrons inside the nucleus of an atom. So the color force was felt inside the protons and the neutrons, but the nuclear force is felt on like outside the protons and neutrons, basically inside the nucleus. So the strong force is repulsive at very short distances and attractive at longer distances. So basically this means that if you remember the range of the nuclear force, right? So it was small. So now inside that range to a certain point, the strong force will be will repel the particles, and that helps in creating a creates the radius of the nucleus, because if it's only attractive, the particles will collide and they won't be able to form protons and neutrons, right? So that's why it is repulsive at very short distances, so that you have a tiny bit of gap between the two nucleons, but after a certain distance it becomes attractive, it becomes very attractive, so that the charged particles, they don't repel each other to, like, because of electromagnetic force, so that it does not repel each other. So it's a very unique force which is both repulsive and attractive depending on the distance. Like for example, electromagnetic force, it can be repulsive or attractive based on the charge. If you have positive charge or negative charge, if there are 2 positive charge, then it's repulsive. If there's 2 negative charges, it's attractive. But in strong force, your repulsive and attraction is based on the distance between the 2 particles. Cool. Okay, so the strong force is, it's strong enough to overcome the repulsive force of 2 positively charged protons, and it does not follow the inverse square law like gravity or electrostatic force. We'll talk about the inverse square law when we reach towards gravity. The carriers of this force is the gluon and the pion, which are also made of quarks. They're not gluons force carriers. We'll talk about pions when we talk more about the Higgs field and the I saw someone raised a hand.
Yeah, I had a question regarding this. Is there a specific point at which it changes from attraction to repulsion, or
yeah,
no?
There's a specific distance. I did not include this because it didn't feel important enough, but I'm sorry for that. But there is a specific distance. I'm sorry, but I don't remember it exactly. I'll search it up and I'll inform you guys in the next session, if that's okay with you.
Sure. Yeah, I just wanted to know if that happens or not.
Yeah. So basically, yeah, cool, no problem. So basically, in that whole range, after a particle goes beyond a certain distance, it becomes attractive. So yes, it is dependent on one specific distance, and after that, it's attractive. Sorry for that. Okay, so a small thing about pions. Pions are basically 2 quarks particles. Like for example, protons and neutrons, they're always made of 3 quarks. pions are always made of two quarks, and one of the and as you remember, the hadrons should be white colored. But in this case, because there's only two colors, you can't make white from the red, blue, and green. So in a pion, you have a quark and the antimatter of a quark. So you have a quark and an antiquark, so that it becomes white, so that it can cancel each other out. So we'll talk about pions later. So they also help mitigate the strong nuclear force as it travels between the protons and the neutrons. The gluons only travel between the quarks, and gluons also travel between protons and neutrons, but pions also do that. So I'm just clearing this out, that pions are not gluons, but they can also indirectly help in mitigating the nuclear force. Okay, any other question? We'll discuss the strong force later when we go into the when we talk about bosons more thoroughly. That time I'll again visit the strong force. Yes?
I do not understand what pions are.
Okay, so pions are also particles which are made of quarks, just like protons and neutrons, as protons are made of different flavor of quarks, that is 2 up and 1 down. Similarly, your pions are also made of quarks, but in this case, they are made of 1 quark and 1 antiquark. Antiquark is basically the antimatter for the quark, of that quark only, so that they can cancel each other out.
Yes, thank you.
Okay, Vidush?
Are pions responsible for mediating the force between the nucleons?
Yeah, pions and gluons both, like they both help, because gluon actually indirectly it's only gluons only, because the pions, the two quarks, like 1 quark and 1 antiquark, they are also controlled by, they also have like gluons which move along each other, which creates the color force. The color force also works inside pions. So pions move around the nucleus. So and like when it joins another proton or neutron, it transfers the gluons there. That's how, like, it's still gluons, but pions are basically taxis.
Okay, like carriers.
Yeah, they're basically taxis for gluons. Okay.
Thank you.
Okay, cool. So next slide. If you guys have any other question, we'll take that also. Okay. Yeah, Urjit.
Yeah, I just have one question. So the last force, the strong force, and under that the color force that we were talking about. So is that so when we talked about that, so that was inside the electrons or the neutrons or the protons.
Yeah,
And
neutrons
when
and the
we did
protons.
talk about the strong force, under that, that is the nuclear force. So that is basically the whole nucleus.
Yeah. So the color force works inside a proton and the neutron. The nuclear force works outside the protons and neutrons inside the nucleus. So the nuclear force is how your protons and neutrons talk to each other. Okay.
Okay. Thank you.
Cool. So next slide. We reach the weak nuclear force. This force has the least range and only acts inside the nucleon. So it only acts inside the protons and neutrons because it has a smaller range. Last force, you saw that it changes it acts both inside and outside, but this force only works inside the nucleon. It is the force that changes a proton into a neutron through beta decay, which is basically releasing an electron in the process. So this force makes nuclear fusion possible and makes the sun shine. We'll discuss about the whole life cycle of a star in a later session. It has two carriers, the W boson, which is charged, and the Z boson, which is uncharged. And the strong force, as you remember, changed the color of the quarks. This force changes the flavor of the quark. We have a video after this. Watch that video, and then I'll handle other questions. Devangi, watch this video, and then
today we continue our series on the 4 fundamental forces of physics. A mere 4 forces that make the whole universe work. And in this installment, we're talking about a force that acts over very, very teeny tiny distances, the weak force. Without it, the sun would not shine. We would not have elements like radium or plutonium, and we wouldn't have carbon-14 dating. All of these things require one particle to turn into another particle through particle decay. Remember strong force? It acts on a proton or a neutron to hold its component quarks together, and one way that we describe quarks is by their color. It's just a characteristic of a quark, sort of like a charge is a characteristic of an electron. Weak force acts on quarks just like strong force does, but instead of changing its color, it changes its flavor. And there are 6 flavors of quarks: lemon lime, root beer, hazelnut. Sorry. Seriously, you've heard of these? Up, down, strange, charm, top, and bottom. Up quarks have a slight positive charge, while down quarks have a slight negative charge, and they both have the smallest masses of all the quarks. The other quarks have charges too, but they're all much heavier and much rarer because they quickly decay into up and down quarks. Up and down quarks are what most stuff is made of. Neutrons are made up of 1 up quark and 2 down quarks, while protons are 2 ups and 1 down. Now the weak force changes quark flavor. So when a quark inside of a particle changes, that changes the whole identity of the particle. This is crazy stuff to me, to think that you can actually, like, just through this force, change a proton into a neutron. It's nuts. In addition to quarks, and thus neutrons and protons, weak force can also interact in a similar way with leptons, the most famous of which is the electron, but also including neutrinos. And as with all fundamental forces, the weak force involves an exchange of particles called force carriers, which are these weird, barely existing particles that convey forces between other particles. Weak force has 2 force carriers, the W bosons, which can be either positively or negatively charged, or the Z bosons, which have no charge. Now, let's watch some weak interaction at work. How about we make a neutron change or decay into a proton? To do this, we're going to need a neutrino passing by. So remember, neutrons are 1 up quark and 2 down quarks, and protons are 2 up quarks and 1 down quark. The weak force is called weak because it only operates within a teeny tiny range, about 0.1% of the diameter of a proton. So say our neutron comes close enough to a neutrino. A positively charged W boson would travel from the neutrino to that neutron. That's the weak force right there. The neutrino, having lost a positive boson, becomes negatively charged, turning it into an electron. And over on the neutron, meanwhile, the positive W boson encounters a down quark and changes its charge from slightly negative to slightly positive. And since neutrons and protons have a difference of just 1 quark flavor, this changes the neutron into a proton. With the composition of the nucleus that contained this neutron having changed, the atom itself has changed too, into an entirely new element. If this was a carbon-14 atom with 6 protons and 8 neutrons, through the weak force, it just decayed into a nitrogen-14 atom with 7 protons and 7 neutrons. And that actually happens. It happens all the time. And it's how carbon-14 dating works. So there it is. The weak force is actually able to change the identity of particles when they come very close to each other. Thank you for watching this episode of SciShow. If you would like to know more about the force.
Okay, any questions? Yeah, Vidush?
One of my questions is, what is is there a fraction for the amount of charge in a W boson?
It's the W boson has plus or minus 1.
Okay. And secondly, is it necessary for a neutrino to be present around a nucleon for it to experience weak nuclear force?
Yes, a neutrino has to be present because the W boson has to come from somewhere, and it's carried by neutrinos. And again, for you can't release an electron from inside a proton because the proton does not have any lepton constituent. So for that you need an extra help. That is where the neutrino comes in. The neutrino gives its boson to the proton. It becomes a neutron, and the neutrino then becomes an electron.
Okay.
So yes, you need a neutrino, and neutrinos are actually there are a lot of neutrinos passing, and they're like very difficult to observe. And neutrinos are very abundant in the universe. In fact, like every second, like billions and trillions of neutrinos pass through every one, like in every second. So right now you're sitting and watching, and there are billions and billions of neutrinos just passing through your body. So neutrinos are very abundant in the universe.
Pantho, can I add just one line with your permission again?
Yes, ma'am.
the about neutrino, when you are saying, I'm so excited to listen this word, because when I learned about neutrino, and I learned that obviously it passes through my hand, and I'm sitting and it's passing through my body, but not harming, and I'm not feeling. So the question was raised in my mind that how come I'm not able to feel it? Point number one. Point number two, from where these neutrinos are coming. This was point number two, because when I say that you are surrounded by neutrino, that's a fact. That is scientific fact, and it has already been proven. But then from where these neutrinos are coming and why I'm not feeling that, these were the two questions which always used to come to my mind. And children, believe me, I explored it, and I found that answer myself. So many times, some points when Pantho sir or Devangi ma'am or Uday sir are explaining you must make a note and you further go, and explore after this class that what is neutrino, from where it is coming. This is a homework. I'm not going to answer, nor Pantho sir is going to answer. From where these millions and millions neutrinos are coming, and they are passing through our body, and they are not interacting, with any of. I'm not feeling that they are. So these two are research questions. Should we give these two research questions to them, Panthu?
Yes, ma'am. You guys can try searching, but I'll warn you guys. Like, it's interesting, but also it's kind of pretty advanced. So there will be a lot of weird math formulas that, like, even in second year, I don't understand what they are.
Yeah,
So
but
those
more
are
or
fun.
less, a little bit, if they research, they will always get some answer, and we will be so happy, Panto, if little bit also they understand
Yes, ma'am.
themselves.
Definitely.
Thank you, Bacha. Please
Al-
carry forward.
Also, what about Z bosons? Do they have any role in weak force? Do
Yeah,
they have any interactions?
Yeah, they also have an interactions. I don't know very well how they interact, but they also have like interactions. So yeah, we'll do it. We'll cover that when we discuss bosons as a much like topic in the next session. We'll cover gluons because like gluons are very important and all. Right now, we are just introducing the forces. We'll cover what does the W boson does in later class, if that's okay with you. Okay. Any questions? Any other questions?
I have a question.
Today we continue our.
Yep. Yep. Go on.
Yes. My question was that last we had in the last slide you had written uh, um, I'm not able to remember the name of the force, but this force changes the flavor of the quarks. How does the force change the flavor of the quarks?
For example, in the video you saw how it changed the proton into a neutron, right? So a proton has two up and one down quark, and a neutron has one up and two down quarks. So to change a proton from to a neutron, you need to change one up into a one down quark, right? And that's what the weak force did. It took a boson from the passing by neutrino, and it went to the it went to the up quark, which now gained a slightly negative value, which then became your down quark. So that's how it, because the difference between up and down is just the charge. That's the only difference that there is between an up and a down quark. So that's how it changed the flavor of the quark.
Yes, thank you.
Okay, enough.
In the video, I think the W boson was showed as having a positive charge, if I'm not wrong. So, can they also have a negative charge or not?
Yeah, they can also have a negative charge.
Okay.
That comes in use when we talk about like nuclear fission in the sun. In nuclear fission in the sun, you also get like positrons. Where like it's a complicated topic, but it's basically through nuclear fusion. They also get positrons, which are basically the antiparticle of an electron, which is just like an electron, just positively charged. That happens when your boson, like the W boson, has a negative charge.
Okay.
Cool. So next slide, next force. Yeah, so now we come to the gravitational force, which we know the most. That is, the gravity pulls everything that has mass towards each other. That is, it is strictly attractive forces. Before this, you saw forces which were both attractive and repulsive, but gravity is always it's a strictly attractive force, and it is the weakest of all the forces. It follows the inverse square law. That is, the strength of the force decreases with the square of the distance between the two objects. So basically, when there's like two objects and they exert gravitational force towards each other, if you increase the distance between the two, the gravitational force reduces between like the object, and it's been seen that it reduces by the square of the distance. So for example, if you change the distance in like 2 units, if there's like first there was Edna, and then you made it 2 centimeter away. So instead of like dividing the force just by 2, it divides the force by 4. Okay. Please, I think there was something left in the last slide. Yeah, so this force describes how stars die and is the entire reasons why black holes exist. Black holes and stars' death, it only depends on the mass of the star. We'll cover how stars die later. There we'll go how it works. And the carriers of the hypothetical particle are the hypothetical particle called graviton. Right now, the standard model does not have any kind of carrier for the gravitational force. Okay, so now we can watch the video.
Today we continue our series on the 4 fundamental forces of physics, a mere 4 forces that make the whole universe work. And in this installment, we're talking about a force that acts over very, very teeny tiny distances, the weak force.
Wait, can you go back? I think I misplaced. Okay, down there you can see the gravitational force video.
Panthu, also you asked kids if they can stay for 10 more minutes so that we can extend this session for another 10 minutes because it's already 6:58. Okay.
I did not realize.
Yeah, and I just am loving the session. I think you guys and your
Today we continue our series on.
Please go ahead.
Yeah. Yeah. Sorry, I misplaced I put the wrong video here.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to read.
Welcome back to our series on the 4 fundamental forces of physics. Today we're talking about gravitation, the force that you and I probably have the closest working relationship with. But it's not only what sticks you to the ground and makes you fall down, it also explains how stars and galaxies form, and it will describe how they die. But even though we can watch it in action, gravitation is much more complicated than it appears. Generally, I think of gravitation in 2 different ways, the way that Isaac Newton described it and the way that Albert Einstein described it. In classical Newtonian terms, gravitation attracts everything in the universe that has mass to everything else in the universe that has mass. And I mean everything from tiny particles to galaxies. It's universal and treats everything the same. But the strength of this attraction depends on the object's masses and the distance between them. The more massive an object, the greater the gravitational force it exerts on another, and the force decreases rapidly the farther apart the 2 objects are. Isaac described it this way: the force of gravitation is proportional to the product of the object's masses and inversely proportional to the square of the distance between them. Newton's mass and distance-based understanding of gravitation is really useful for stuff like predicting the existence of Uranus based on the movement of Neptune, but it doesn't explain everything, like Mercury's orbit. Trouble with Mercury is that the point where it's closest to the sun, its perihelion, isn't where Newton's law predicts. It took an Einstein to explain that. Actually, it took Albert Einstein. Einstein described gravity as a property not just of mass, but also of space and time. He envisioned space-time as the fabric of the universe, and his theory of general relativity basically says that objects that either have mass or energy distort that fabric. Think of a watermelon and an orange on a mattress. Each makes a depression in the mattress, and if the orange rolls toward the watermelon, it will accelerate as it reaches the depression made by the more massive fruit. The attractive force thus gets weaker or stronger depending on the distance between the fruits. It's like Newton's law on steroids. Gravitation is the warp in space-time created by mass, or energy. So in the case of Mercury, the closer it gets to the sun, the more the sun's huge mass curves space-time, which effectively causes that point of perihelion to move. You'll notice that this applies to objects with mass or energy. Einstein discovered that gravitation can also influence energetic but massless stuff like light if the force is strong enough. For instance, he observed that light bends around really massive planets and stars, and his theory of general relativity predicts correctly that a compact enough mass could distort space-time so much that light could not escape it. And that is a black hole. Now remember that for each fundamental force, there is a particle, a force carrier that essentially conveys force between bodies. But if light responds to gravitation, its force carrier must be really tiny. Gravitation is described as being carried by massless particles called gravitons, but unlike other force carriers we've talked about, like pions and gluons, gravitons are theoretical. They've never been detected, and they are predicted to be essentially unobservable. We're only able to witness their handiwork, and that is gravitation. We hope that you enjoyed our series on the...
Yeah, any questions?
I think Alia's hand was up.
I had actually not put down my hand from the last time. I'm so sorry.
Okay, so
It's
did
okay.
you? It's okay. Did you understand the thing, Alia, or you need clarification?
Ma'am, I understood.
Okay. Any more question?
No, ma'am.
So over to you, Devangi. I can see Professor Kenji here. You can welcome here and to let him address students for a few minutes and let him. Thank you.
So we have Dr. Kenji with us today. I would like to welcome him to the session. Sir, could you speak for a few minutes? It would be really great.
This is important to say that the children are from different grade, from 6 to 12. And I think Dr. Kenji is in mute. Can we hear from you, sir?
Yes, yeah, I can hear you.
Yes, Dr. Kenji.
Yes, ma'am. Yes, sir, we can hear you.
Yeah, this is my comment.
Yeah, we would like to know from you because see the children are from all different grades from 6 to 12 and these three teacher peer tutors are fabulous and also Rachna ma'am who has mentored. Can we have all three tutors on screen? We would like to listen something from you. The audience is just too good, Dr. Kenji. They are from grade 6, 7, 8, 9, 10 and they all are asking and they all are updating their knowledge on fundamental of particle physics from your team. So we would like to listen from you, Dr. Kenji, that how do you, what do you feel about the sessions? Thank you.
Yeah, okay, thank you. I as much as I briefly and listen to the session, the speakers and well, prepared and concisely present the basic aspects of the particle physics. Yeah, it is. I think that such lectures will help for the people who would like to know the very basic of the particle physics without no technical difficulties. Hello?
Yeah, thank you, sir. Thank you, sir. Any suggestions for us for the next few sessions? Some things that we should keep in mind, and anything that you would want us to cover?
I think that as the current purpose and the very introductive and course, and maybe in the current way looks nice. So which topics you choose is maybe, yeah, it is how to say, yeah, some, yeah, of course, in principle many topics, but you selected some important ones. I think this is fine. Yeah. For
Thank you,
this
sir.
part. Yeah.
Thank you, sir.
So, Pantho, is there some home assignment, or you want them to research on something? So you can end session in last another 2-3 minutes. So that this, and also please announce that all those who have missed, in the beginning, they can see this on the YouTube. We will be uploading the whole session on YouTube also. Thank you.
Yes, ma'am. Yeah, Ariman, you have your hand raised.
Yes, I wanted to ask one thing. What is the function of the neutrinos?
The neutrino, they don't as such serve any purpose in your day-to-day lives. It just sometimes it through weak force, it sometimes changes into a neutron and it creates it. It does that, but other than that, it does not serve a lot of purpose.
Actually, I
Yes.
found something on Google that it finds or detects the presence of dark matter.
Yeah.
What's the name of this kid? Madhav?
Yes, ma'am.
Brilliant question, I must say. And we will explore more. And you are right, it detects on also the presence of neutrino can be felt, not by us, but whenever there is a nucleus disintegrates, whenever there is a change of, or whenever the beta particles and all those things, your seniors will cover in the later on section. So neutrino plays a very, very important role. So maybe probably in next session we will cover all this. Pantho, is that okay? Because
Yes, ma'am.
probably you can show with one equations that how neutrino and antineutrino etc. In how the decay of particle, how they contribute their contribution. And obviously there is a topic on dark matter on one day, and we will cover all those things. Thank you. Over to you, Madhav. You want to ask anything?
No, I don't have any question.
Over to you, Pantho.
Okay, we'll cover dark matter. That's probably the last session, the last topic that we'll cover in this session. There, I'll remember. I'll try to cover this topic. So with this, I think this session is adjourned. I would like you guys to, if you guys have any questions, you can mail us. You can mail either me, Devangi, or Uday. I think you all have our email IDs, and you can search about the neutrinos on your own. And
what were the research question, Rachna ma'am? What we have told the students to research? Today's research question.
You guys can also research about the Z bosons.
Yeah.
Ma'am, I think you said that where do the neutrinos originate from and why do they not interact with the body?
Yeah. So the two research questions, from where these neutrinos are coming, and when we say we are surrounded by neutrino, from where these neutrinos are coming, and second is if they are passing through our body, why can't we feel it? So these are the two research questions. You just research and come back for the next session. Over to you, Pantho.
Yeah.
Vaishnavi.
I guess that's it. Yeah. Any question?
Sir, can you repeat the homework which you just now said for the research?
Okay.
Can you repeat the question?
Yeah, I think she wants to repeat the questions. Devangi, can you?
Yeah. So where do neutrinos originate from, and why do they not interact with the body? Is that clear?
Yes, and thank you, ma'am.
Yeah, and also you guys, if you want, then you can also search about the the Z bosons. I guess, yeah, that's it from us today. We'll meet we'll meet on Saturday, same time for the next session.
Right. So we would be covering particle accelerators and a little more in the
Yeah,
next.
Devangi will be covering particle accelerators and other stuff.
Okay, I'm really excited.
We're happy we could help.
Yeah.
Can we have one
Okay, so
screenshot of many students are there on video on? Can we have one screenshot of kids, at least 4, 5, and obviously Dr. Kenji is also there. So, just one screenshot, Devangi, if you can take, just to motivate others so that we can share this with my mail. Thank you.
Yes.
Children, will you please open your, switch on your videos? Thank you.
Yeah.
thank you, sir, for coming to this session, and
Please
thank you, sir.
take a screenshot with Dr. Kenji too.
Yes. Yes. Right. I took the screenshot.
Yeah, thank you.
And Dr. Kenji, on behalf of Team Nucleus, it was such an honor and a pleasure to have you with us today. Your presence has really, inspired all of us a lot. And I'm sure especially our student tutors who, as you can see, are already putting in a lot of effort. And your presence, I guess, has motivated them to still better themselves in the next session. So we are very, very thankful to you for this.
Yeah, welcome. Yeah, thanks.
I think students are glued to the screen and many of them have not still left. So children, there's a homework. Please see all the videos. We are uploading all videos on Google site. And probably Panthum, you just take a quiz. Next session, 10 minutes fast quiz.
Yeah.
You know? So,
Yeah.
and
Yes,
then
ma'am.
maybe
Yes, ma'am.
select the winner and runner as well. I mean, maybe 3, 4 winner and 3, 4 runner. Why not? We just need to encourage children to go through the video, do research, and come back. Thank you.
Yes, ma'am.
Yes, ma'am.